Thanks to the Talk Python team who sponsored this episode of the Engineered Mind podcast. If you want to learn Python and delve into exciting topics like data science, web development, or building apps, feel free to visit talkpython.fm/mind to find your next level and get a 10% discount. Also a big thank you to all my patrons who support the Engineered Mind podcast. Hi and welcome to the Engineered Mind podcast. In this podcast we cover topics such as engineering, artificial intelligence, neuroscience, and other interesting topics to educate, inspire, and engineer people's minds all around the world. I'm your host Yusuf, and for this episode of the podcast I'm very excited to have Jon Krohn on my show. Jon is Chief Data Scientist at the machine learning company Untapt. He authored the 2019 book Deep Learning Illustrated, an instant #1 bestseller that was translated into 6 languages. Jon is renowned for his compelling lectures, which he offers in person at Columbia University, New York University, and the NYC Data Science Academy, as well as online via O'Reilly, YouTube, and his podcast, the artificial neural network New Network. Jon holds a Ph.D. in neuroscience from Oxford and has been publishing on machine learning in leading academic journals since 2010. We talked about issues like the company Untapt and how AI-powered recruiting works. How much did Jon's background in neuroscience help him in AI? Where to get started when learning machine learning? Tips for becoming a deep learning specialist? And what is Jon most excited about in terms of AI? But also how we came up with the idea of writing a book. For updates on upcoming podcasts, projects, and videos, make sure to follow me on Twitter as well as on Instagram. And now, ladies and gentlemen, here's my podcast with the one and only Jon Krohn. Jon, welcome to my podcast. Very nice to have you on my show. It's an absolute pleasure.
It's an honor to be here, Yusuf. Thank you.
Thank you so much. And I want to jump straight into Untapt. Can you explain what is Untapt and what are you doing at Untapt?
Sure. So Untapt is the company that I'm the chief data scientist at. We build models that automate natural languaging aspects, specifically in human resources. So we've developed a niche over the years, initially by running our own recruitment website, in which we accumulated a large number of decisions of whether a given candidate was invited to interview at a different job. So hundreds of millions of decisions accumulated over the years. And then we've been able to use that data set to build state-of-the-art APIs, leveraging deep learning and other natural language processing techniques in order to automate the repetitive, boring parts of being someone working in human resources or working as a recruiter. So as some examples, we have a lot of clients that are big corporates that get millions of applications a year to thousands of different roles. And to give a really good example of how our technology can help, one of our clients did an internal investigation comparing our model against their state-of-the-art approach, which was using a really sophisticated Boolean keyword search to look for candidates. And our approach identified 21 times more of the relevant candidates out of their database of millions of candidates. And so that, you can imagine, they were getting 5% of the people that were qualified for the role that they were trying to fill. So that gives you a sense of what we're able to do. And it also means that their internal recruiter doesn't need to be coming up with some kind of Boolean search to try to find the person. They can just throw in the resume that they're trying to fill, or they can throw in the profile of a candidate that's relevant to the role that they're trying to fill. And our system can automatically and instantaneously go out and look over all the millions of profiles that they have and give you a result back, ranked based on the probability that any given candidate will be invited to interview at any given role. Mm-hmm. Which also is better than the kind of Boolean approach, because with a Boolean approach, you get a binary yes or no. And so even on that 5% of the results that they were getting back, they don't even have a sense of where to start in there. You have to go and look at every single one instead of starting at the top of the list.
Mm-hmm. Get it, yeah. But so is it right that you switched from some kind of a recruiting consulting kind of company to more of a software company? Because as you talked about these big corporates, right, they have their own, their own teams of data scientists who actually are experts already. So you can provide them with the API or however you do that.
Exactly, that's right. So with clients that are big corporates like that one I just mentioned, they're a microchip company. And so, as you say, they have lots of data scientists already. They have a team of HR data scientists. And so they ask for an API, and then they can integrate our API into their existing systems. So that gives you the sense of like kind of the big corporates. Another segment of our clients is big recruitment companies. So they are similarly needing to solve these kinds of problems where, you know, in the case of the recruitment company, they might even have more examples of how our models can help. So they might have many inbound resumes. They might have thousands of resumes coming into their system every day. And we have built custom models for our recruitment clients to take that document and then notify the most relevant consultant that they have at the company. So they might have thousands of consultants, but let's say you're working there and you specialize in recruitment for data science, and then data science resume comes in as one of the resumes that day, automatically we can send that resume to you. And unlike the corporate clients, the recruitment company clients, they tend to not have in-house software developers. They don't know what to do with an API. So we also have people at our company that customize user interfaces for those kinds of companies. So depending on their need, we can build a very big system that does a lot of different things, or we can take a relatively off-the-shelf software system that we've already built and maybe just white label it for their purposes. So exactly, so we do kind of, as a lot of AI companies do today, we do a mix of consulting and developing products, and we can use the consulting as an opportunity to develop better and better products. And over time, we have more and more products that can be more gently adjusted to fit more clients' needs.
I like that approach. I don't mean it in an insulting way. Is it like that you are the better LinkedIn somehow?
In a way, I mean, typically it's really a different part of, for the most part, it's a different part of the life cycle, although in some ways we do compete. So it depends on what the client needs. So very often, if they're a big recruitment company, they're going to have LinkedIn seats as well. They're going to have the paid LinkedIn recruiter seats, and they're going to be using LinkedIn to source candidates. And it's as they source those candidates and they're kind of ingesting them into their internal system, they've started to work with those candidates directly. They've built up a lot of rapport. They have lots of notes on the candidate, what their salary is. All these kinds of things can be stored in our system that we built for them. And then all of those candidates are stored in their database with our user interface sitting on top of that database. And then we can use the algorithms that my team builds to easily look over their existing database and say, okay, you have 400,000 candidates. A client of yours, a big bank, has opened a new requisition, and instantaneously we can go and look over that whole database and provide candidates to the relevant recruiters. In fact, one of the coolest new products that we've built, it works like the Facebook newsfeed, where the recruiter can show up at her desk in the morning and we show a newsfeed full of tiles that say, hey, you've got this current opening. Here are some new candidates that just showed up overnight that look like they're relevant for the role. Do you think they're a good fit or not? And then we can use those labels that she provides. Her decision if this is someone that is a good choice or not. We can use those to further refine the algorithm for that specific role. And we can, right there in the user interface, she can choose to message her client or message the candidate or even phone, either or. So it's this way of kind of centralizing and automating and pushing prompts so that recruiters can focus on making the phone calls as opposed to searching or trying to identify the right fits for a role.
Oh, that's super cool what you do. I like the approach. I can imagine, because you mentioned earlier on at the beginning that you have a lot of data, so the parameter space is quite complex, I would say. What parameters are, maybe you can name a few, that go into this big investigation? Let's call it like that.
Yeah, so there was a time when I started as the chief data scientist at Untapt 5 years ago. So I'm now the oldest employee in the company. The company's 6 years old. And so I joined after about a year. And when I first joined, they had a very simple heuristic model where they were using their expertise, at that time, they were filling a narrow set of roles in a relatively narrow industry. And the founders of the company had expertise in those spaces. So they came up with this heuristic model that could look for keywords and assign a rough score, just an integer value from 1 to 10, saying this is probably a good candidate or not. When I joined, I started taking those features that they developed and putting those into regression models. And so this was kind of a simple, in the beginning, we only had tens of thousands of decisions. And so this kind of regression model, putting in a few dozen manually curated features, in the beginning, this was good enough. But as our data set became larger and larger and larger, and as I became more and more familiar with using deep learning for applying natural language processing techniques, and experimenting with those more and more, we eventually got to a point where we do not provide any manual features to the model anymore. So we use an entirely data-driven approach where we rely on the deep learning model itself to identify what the most relevant features are.
Got it. You also mentioned that when you have the big corporates and they have the data, just to clarify it, can there be some kind of synergy effect between your approach, your existing data set, and those of big corporates?
Totally. So something that I glossed over is that some of our clients are happy for us to use their data to train the whole pool. Okay. So those hundreds of millions of decisions, we didn't get those entirely ourselves. Many of those decisions were also acquired from clients that said, okay, you can use anonymized versions of our data for further training your model, for example. And there are other clients, however, who are, they have much higher security concerns where we have to have dedicated servers in an isolated system for their data only. Their data can never leave the system. We can never train our general algorithms with their data, but we can use transfer learning to fine tune with their data based on our larger model.
Okay, I see. In your area, who are your biggest competitors at the moment?
There are many of them. So there are, we had a client, one of our biggest clients, they did a search for a vendor like us that could do matching, and they identified 200 companies, and that was a few years ago. So they identified 200 companies worldwide that were doing this kind of AI matching, and we came out on top of those 200. There are lots of companies out there. There are other companies out there that are much bigger than us. So in that sense, I would say they're our biggest competitor because they have a much larger client base. And typically, these are companies that have specialized for decades in parsing resumes. So taking the Word document or the PDF and parsing that into some kind of structured JSON or XML file, where it says experience entry and then the dates that they had that experience entry and so on, what university they went to, what degree they got at the university. So the companies that have been specialized in doing that kind of parsing over many years, and they already have a firm foothold in many big companies, those companies have begun to offer matching algorithms as well. However, we have experimented with many of those kinds of algorithms. The results are far worse than with our approach. And a big reason is because, one, those parsers tend not to work very well. So they often don't get the right information in the right places. And the second thing is that they will use a keyword-based approach. So although it isn't as simple as this, it's a slightly sophisticated keyword search. So what they do is they can ingest a job description, and then they have these manually curated lists of keywords where things like Java, C++, they have those keywords identified as software skills. And so then they go look over every job description and pull out all of these keywords. And so they say, okay, this person has Java, C++, Python. This person is probably a software developer. And then they can go over, look over the candidate profile and see which candidate profiles have extracted those kinds of keywords as well, those exact keywords, Java, C++, Python, and the candidates that have the highest word count of those keywords matched with the job description that has the highest count of those keywords, that will show up as the best match. And so it isn't a very sophisticated approach. It means that a candidate who is more creative on their resume will be missed, because if they use synonyms to describe what they're doing, that won't get caught.
Yeah.
It also means that candidates that are creative, even with the formatting of their resume, will be missed because the parser won't parse it properly. And so our approach provides much better results, but fewer people know about us at this time.
I see. I'm trying to spread the word for sure. At least I'm trying.
Man.
Yeah, no worries. You also mentioned now the programming languages. I know that you do a lot of teaching. Like I see you almost everywhere. Like if it's in O'Reilly, you have the great book which we'll talk about in a few moments. What programming languages would you recommend for someone getting started? And do you see another programming language being the dominant one in the near future?
That's a great question. It's my answer is going to be unsurprising. I think that there's little point. What language am I going to say? What is the one to start with?
Let's say Python.
Yeah, of course. It's and that is going to be the language for the foreseeable future. That is the most important language to know in data science, particularly if you're getting started. There are lots of other languages that, for specific reasons, you might want to also specialize in. So a lot of data scientists learn R, and R can be great, particularly for data visualization. I think that the data visualization tools like ggplot2 are much more sophisticated than the best visualization tools in Python, which is probably Seaborn. So I think that that's one way to go. Also, if you want to be building kind of interactive visuals, you could even start getting into something like d3.js. And that's a really cool way of surfacing visuals. If instead of going down the visuals route as a data scientist, if you want to go down the route of kind of a more of building more efficient algorithms in production systems, then maybe you want to be learning C++ or C. So I think Python is the starting point, and then depending on where you want to specialize after that, more towards the front end or more towards the back end, you could specialize in other languages, eventually maybe learning the whole stack.
That's great advice. And you also have a background in neuroscience, if I'm not mistaken, a Ph.D. in neuroscience, actually. How far did the background in neuroscience help you, like understanding, grasping the concepts of AI better? And if you can maybe explain it, did you have projects where your background in neuroscience actually really helped? Where you said, okay, that's from neuroscience, that helped me here. What would you say? Yeah,
it's kind of a coincidence. So I did my PhD in neuroscience, and at the time that I was doing it, there was one guy I knew who was using artificial neural networks to analyze his data. I didn't touch them in my entire PhD. I used lots of different approaches. I did a lot of Bayesian statistics during my PhD. A lot of regression modeling, a lot of causality modeling, decision trees, random forests. And so my PhD was a place I decided early on in my PhD, there were other people in my year who became specialists in putting electrodes into the back of ferrets' heads and recording from the brains of ferrets. There were other people who became expert at running brain scans, and other people who became expert at growing tissues in a lab. And I decided right at the beginning of my PhD that it made the most sense for me. I guess I already had some experience with computer programming, particularly statistical programming. And so that to me seemed like the most obvious thing to specialize in. And so I spent my PhD developing machine learning skills and computational statistical skills because I think it's the most fun. You get the results most quickly. You can design an experiment in a day and have the results that day. Whereas if you're doing one of those other experiments I described, it might take months or years before you get your results and figure out how you're going to iterate and keep going. So I thought this was a really great idea. And it ended up being a cool thing because by being specialized in computational statistics like that, people would come to me from across my research center and say, hey, I have these results. I think I see a pattern, but I'm not sure how to analyze it. And so I helped a lot of people analyze results for their papers. And so I got a bunch of really great publications out of my PhD, where frankly, I didn't have to spend that much time on it. Like they might have spent months or years generating the data, and then I spent like days or weeks getting results in a publishable format.
I see. Talking about publishing, let's jump to your great book, which I also have, by the way. How did you come up with the idea? Because there's a plethora of books out there talking about deep learning, machine learning, artificial intelligence in general. What was your motivation to have a book like that? And also, why did you use these cool illustrations that we can see inside the book?
Yeah, so I realized that, going back to your earlier question, I realized I didn't actually really answer it, because you asked if neuroscience, and this kind of ties into the book answer, but you asked, so I ended up in my PhD focusing entirely on machine learning, but not neural networks specifically. And then it was after my PhD, after I'd been working for a few years, that in 2012 we had AlexNet win the ImageNet large-scale visual recognition competition. People started to become aware of deep learning. And so I was like, oh man, I really need to learn this stuff. And I was particularly fascinated. There are elements, whenever I came across a relationship between biological neuroscience and artificial neural networks, deep learning, that did excite me. So I kind of gravitated towards those examples. And so starting in the 1950s, biological neuroscience, specifically an area of it called computational neuroscience, set about building these artificial neural networks as a way of trying to get an understanding of the way that the biological brain works. That inspiration, now many years later, has resulted in these advances in the way that we do machine learning. So deep learning approaches, they grow out of that academic biology tradition. However, for the most part, the relationship today is tenuous. So while biology continues to inspire advances in deep learning, it is really just an inspiration. It isn't like a faithful replication of the way that a biological system works. But I think that that's really cool. There are a lot of people. So Google DeepMind, for example, in London, they have on their staff, they have many neuroscientists who specialize in the biology, and they're probably the leaders in the world of trying to figure out how to take those inspirations from biology and get some kind of positive improvement in results based on that biological insight. Anyway, so I did in Deep Learning Illustrated, I do highlight those biological inspirations wherever I can. However, that's kind of where my background in neuroscience and deep learning kind of ends. That's all there is to it. The book, really, I got started with teaching deep learning. Initially, it was with having a study group to go over deep learning textbooks and lectures as a group. So I learn a lot better when there's a deadline and when I have to be accountable to people, and I know that about myself. So I started this deep learning study group where we would come up as a group with, okay, in 2 weeks we'll meet again and we'll have read these chapters. And I knew that because I was hosting the meeting, if nobody else wanted to talk about it, I was going to have to be standing up at a whiteboard and explaining it. So I'm going to have to read it and really understand it well. So that's what I did. And after doing that for about 6 months, I was like, hey, I have quite a bit I'd like to talk about here. I think this is really interesting. And so that was late 2016. I started speaking in New York at meetups. And deep learning at that time, a lot of people knew what it was, but hadn't done very much in it. And so a lot of these meetups, I was their first deep learning speaker, and nobody knew who I was at that time. But I could sell out. The meetup organizers would say, we've never seen an audience like this. They'd have people lining the walls. So they'd have an overflow room with a video camera. And so I was like, wow, this is something people really want to hear about this. And that got me excited about the idea of writing a book. And at one of those meetups, there was an editor from Pearson, the big textbook publisher, and she asked if I'd like to have lunch and talk about it. And I was like, absolutely. I've been thinking that would be a good idea.
That's cool.
And so, and then it took a few years. I've made a bunch of videos for Pearson. I've made like 30 hours, maybe 35 hours of videos for Pearson. And some of those have been really popular in the O'Reilly platform, like you mentioned. And that helped me, figure out how I was going to write the book. And then the book was so through my experience of running the deep learning study group, of making videos on deep learning, I teach deep learning in many places. So I have a comprehensive curriculum that I offered at something called the New York City Data Science Academy, which is for professionals. So often their company will pay for them to come and kind of reskill in say deep learning. So I have a 30-hour curriculum that I offer there. And then I guest lecture at Columbia University and New York University. And teaching online with O'Reilly. So by all of these ways, I developed this experience of, okay, how can I most clearly communicate these ideas? And what I found was that using visuals, colorful visuals, so using as many different whiteboard colors as I could to kind of explain concepts and how things relate to each other, that this was the way that students responded best. And so then the textbook follows that. And I think it is, I haven't seen a textbook like Deep Learning Illustrated, and I'm open to somebody showing me one, but where all of the equations are in full color, where the colors in those equations relate to diagrams, and those diagrams depict how the equation works. And even having kind of fun illustrations, like, I don't know if you've seen in chapter 8, we use this, it's actually, I think about it being in the Alps, near where you are, of this, we have a trilobite.
I saw that one.
Yeah, they're like the mascot of the book, and we have a trilobite, in this case, with a hiking backpack, with a rucksack, and with a kind of a Bavarian hat with a feather in it, going out on a hike. And he starts the hike at a random point on a mountainside, and he knows that he lives at the lowest point in the valley, and so he needs to find his way to the lowest point in the valley. But the trilobite is blind, so he can't just see in the distance where it is. So all he can do is use his cane and look in the space around him. And okay, if whatever space around me goes in the lower direction, I'll take a step in that direction. And so this is this visual analogy of the way that stochastic gradient descent works. So it's this kind of thing, these kind of visual approaches that I had a lot of fun making, and that people have been responding to in the book.
I think that's a very good approach, because the human itself, the brain, is quite powerful, but when it comes to higher dimensionalities, it's quite hard to imagine what is a fourth order tensor, for instance. It's a bit weird to imagine. So having geometry and stuff like that, which you mentioned in the book, is quite useful. You also offer, when I saw on your GitHub page, you offer some code bases, like, for instance, IPython notebooks. Then you have these code bases. It's kind of that we have this narrow intelligence still, that specific code is tailor-made for one specific application. How is it when you really work on stuff that you can use one code base and use it for another project? Is it something that practitioners do, or?
In deep learning, it happens a lot. So in deep learning, nobody knows what the very best modeling approach is for any problem. And so even some problems that are quite old, like identifying handwritten digits this is a problem that we've had a good data set for since the 1990s. Still, people every few years come up with a new machine vision model architecture that can do even better than the previous results. So we never know when we've reached the theoretical maximum of performance. And because in deep learning in particular, there is an effectively infinitely vast hyperparameter space of all of the different kinds of model architectures and gradient descent training approaches, and how many layers we have, what layer types they are, how many neurons there are in a given layer, what kinds of normalization approaches we use, how we pre-process our data. It is infinite. It's an infinite number of possibilities. And so when you go to start tackling any particular new problem, as a deep learning practitioner, if you don't already have a lot of experience solving similar problems, you'll probably go and look in GitHub and go look in archive and see what other people have been doing to tackle problems that are similar to yours. Use that as a starting point. Maybe there will be some things about their architecture where you say, hey, based on the problem they were solving specifically and the problem I'm going to be solving specifically, I need to be doing my pre-processing a little different.
Mm-hmm.
Or maybe their architecture is way too deep. I have way less data, so I'll take a few layers off. So you kind of develop this intuition as you practice deep learning more and more and more of taking existing architectures that people have used and getting inspiration from that and adapting them to your problem.
I see. It's nice that you mentioned it because when started with deep learning or AI in general, and you gain the experience like yourself, you teach, you do this, you do that, and in neuroscience it's called, as far as I know, neuroplasticity. So you do you see in the future that codebases have this kind of ability /AGI? Do you think that will come, or are you someone who says I'm living in the here and now, and what's in 10, 50 years maybe it's not that important for me? How do you see that?
Well, Yusuf, that is a very interesting question, and there's a lot of ways I could answer that. I guess, in a way, you could think of at least what we have today. To use your analogy, it's human agents who act as the things that confer that neuroplasticity.
Mm-hmm.
Although you could even use, so it depends on, because in an even finer level, so you're thinking of the neuroplasticity there as something that a human agent is changing model architectures, model hyperparameter aspects.
Mm-hmm.
However, on an even finer level, you could think of learning as a strengthening and weakening of connections between neurons.
Mm-hmm.
And this is already what we do with backpropagation and stochastic gradient descent. So at that very fine level, we've actually come up with a pretty good system for having a machine learn from examples and have that neuroplasticity at that very fine level. And then if we're talking about a larger level, the human is kind of like controlling. It's like taking a human's brain and then giving it a stroke and like taking out one part and seeing what happens. Or taking two brains and linking them together and seeing what that happens. So there's kind of this like extreme neuroplasticity that human agents today are controlling in terms of the model architectures. But then there are also lots of existing tools for doing thoughtful hyperparameter searches. So there's tools, one that I really like is called Spearmint, which uses Bayesian statistics to try to approximate what the best hyperparameters might be for a given model. Mm-hmm. And so it's somewhere in between those two extremes of the human giving strokes and the stochastic gradient descent learning how to weight connections. Then in terms of your kind of long view question of AGI and that kind of thing, of algorithms that could have truly insightful, creative ideas about how to build new models. That's basically what you're saying, is like an algorithm that could read archive papers and come up with a completely new kind of architecture that we've never seen before, probably.
Mm-hmm.
I mean, that's an exciting idea.
It's very cool.
There's no roadmap to anything like that today. It's not, that can't even be imagined in some realistic sense of like, oh, that's what I'd like to achieve. What are the steps to get there? And how do I do it? We are very far away from that. Today's machine learning algorithms are truly very, very, very dumb. They make 1-year-old children and dogs look like brilliant geniuses.
That's right. You also talked about backpropagation. As a neuroscientist, do you think the brain uses backprop? Because I talked to another computational neuroscientist, and they say, or neuroscientists in general say, the signal is only transferred from one point to another, and there's no backward signal transport, as far as I know. Maybe you can comment on that.
Yeah, I don't think that there isn't something that is specifically like the backpropagation mechanism that we know of in the human brain.
Mm-hmm.
It is only in a very vague kind of sense. If you thought about, so for example, when you develop some advanced skill, like becoming very good at badminton. You've never played badminton before. In the beginning, you are recruiting you're using a relatively small number of brain cells, some initial brain cells, and you're having to focus very hard to use those effectively to learn the basics of badminton. But then as you develop those basics, those connections become stronger for the basics. And then that kind of gives you the capacity to then kind of learn the intermediate things. So more neurons can be recruited into your kind of badminton specialization network that you're developing in your brain. And so in that way, that's kind of like vaguely like backpropagation. If you think about it as like, you know, one of your layers in your neural network, if you're trying to build a machine vision network, you can't have representations of very sophisticated visual representations, like what a face looks like, until you've had earlier layers that have figured out what straight lines are like and how to make those straight lines into curves. So I don't know, there's kind of that vague analogy, but there's nothing even close to exactly the way the backpropagation works and the biological brain works.
I see. Okay. Jon, what I want to ask you is if some newbies are listening, want to get into the beautiful field of AI, what tips would you give them before also creating a study group and have to go through several papers and books? What tips would you give them if they want to get started in AI? Where's the best place to start? Of course, apart from your great book, what would you tell them?
Yeah, I mean, I built my book for that person. So my book is designed for that person. So, you know, I'll answer your question more broadly right after, but the book is really, I think it's the best resource. So by having the study group and by teaching deep learning to so many different groups, I have kind of gathered together all of the best information that I know of for getting started in deep learning. And so with Deep Learning Illustrated, I've organized the book so that the first part of the book, the first 4 chapters, even somebody who can't code can go and read those 4 chapters and understand what deep learning is and what kinds of problems deep learning can be used to solve today across machine vision, natural language processing, artistic creativity, and complex sequential decision making. So, and then in the later parts of the book, we start to get into code examples, and I provide lots of resources in the book for getting started on your first projects and where you might want to go from there. So I really do think it's the perfect starting point. However, if that isn't your cup of tea for whatever reason, I have on my website at jonkrohn.com/resources, I have at the very top of that page, at least today, I have like recommended pathways for getting started in deep learning and in data science. And of course, I talk about my resources, but I also talk about other people's resources as well, including other people who have provided lists, recommendations of how you could progress through. And so that's a great place to look as well.
Thanks a lot. And I will link everything down in the description, as well as the code, if it's legit, to the affiliate code from you to get your book as well, and also link to the nice podcast that you have, the A4N podcast. Yeah. As a practitioner, do you have 3 tips, let's say 3 tips as for now, for deep learning's practitioners? What is the thing that people are more struggling with at the beginning? What would you say?
So I've actually just begun. You're one of the first people that I'm telling about this. So over the last few years, from 2016 to 2020, early 2020, most of my learning and my content creation has been on deep learning specifically. Through those years of teaching the material, the biggest gap that I identified was in people's understanding of the foundations that underlie machine learning. Okay. Linear algebra, calculus, probability, and some computer science, algorithms, data structures, optimization. Okay. And so I'm starting now on building, eventually it will be a book called Machine Learning Foundations that covers all of these topics and specifically relates them to building machine learning applications. And so I'm starting off already now beginning end of May in O'Reilly, I have my first lecture. It's like linear algebra 1, and then a week after it's linear algebra 2, and then after that is calculus 1. And so it's going to be 8 3.5-hour lectures that I'm giving in O'Reilly from end of May to beginning of September. And that series will hopefully at the same time, I'll have enough extra bandwidth on evenings and weekends to also be producing videos in YouTube. And my current thinking is that most or maybe even all of the videos I'll publish for free on YouTube so that everybody can take advantage of these resources. And yeah, so I think that was a long answer to your question, but basically it's the foundations. A lot of people, whether it's deep learning or other machine learning approaches, they have learned how to take scikit-learn code or Keras layers and use that abstraction.
Mm-hmm.
But if you want to become a much better practitioner, you do need to understand what's going on under the hood, because otherwise you might not appreciate where you're making critical mistakes or where there could be room for much improvement.
I see. It's so cool that you said that, because I'm also working on a beginner's guide for linear algebra, but it's not as sophisticated as yours, which I think. So I want to know from you.
You're making a beginner's guide to linear algebra?
Yeah, exactly, for my small channel.
That's really cool, man. That's so fun. I can't wait to check out what you do. I mean, because I'm right now, like this week, most of my working time this week, I've been completely immersed in linear algebra, making the materials for this first course. And this, I mean, it starts right at the basics. I'm sure it's the same kind of, eventually it will get a little bit more complicated, but like, in the beginning, it's just like explaining what a tensor is and explaining what a matrix is and what's the right notation and how do we build them in NumPy and TensorFlow and PyTorch.
Exactly. Yeah, it will be cool.
That's cool. I look forward to seeing what you do.
Yeah, sure. I'll share it with you then. I want to know from you, which is the last question as for now, what are you most excited about in terms of AI?
Oh, man. Well, I'm hopeful that machine learning can do a huge amount of good for society. Mm-hmm. So if you look back to 1880, which isn't that long ago, people were, anywhere you looked in the world, even in, at the time, what were some of the most advanced civilizations. So if you looked in England or France or Germany, the people who lived there, you didn't have antibiotics.
Yep.
95 to 99% of people were involved in agriculture and would miss meals and were starving. Something like 5% of people were literate in even those relatively advanced civilizations. And in the past 150 years, all of those things have flipped on their head, thanks to automation of machinery. So agriculture, now in the US, is 1% of people employed in it instead of 95 to 99%. People have to be literate. So instead of 5% of people being literate, 95% of people are literate. So all these things have turned on their head. Mm-hmm. And so mechanical automation has already played this huge role. And now, as we accumulate more and more data, 5G rolling out, self-driving cars and all the data that they create, every 18 months, the amount of data stored on the planet doubles. Mm-hmm. It's crazy. And machine learning algorithms are capable of harvesting patterns from those data, and we can automate more and more things and free up more and more time for solving, instead of being involved in the relative monotony of, accounting, people can be thinking about big scientific problems or big artistic problems, or just maybe enjoying life. Maybe maybe a large proportion of society will be able to live in leisure and not have to work at all. And so I think this is really exciting. I think that we already live in by far the most peaceful, healthy times in history by an enormous margin. And I think that the shift from mechanical automation towards cognitive automation, that this should it should be even more beneficial, and we could be living in a really a really interesting, peaceful world.
Yeah, I completely agree on that one, Jon. Thanks a ton. Is there anything else you would like to say to the audience? Of course, I will put the link to your great homepage down below, to your courses, to your book, and so on. Is there anything else you would like to tell the audience?
I don't know. That's a very open-ended question. I guess something that I try to say, and something that I say at the end of a lot of the video series that I make, and that I say at the end of the book, and that I kind of even alluded to in the last thing that I said. If you can make the time or be able to focus some of the energies that you're spending on machine learning or data science, if you can afford to spend some, or maybe even in some people's cases, a lot of your time on trying to solve social problems, I think that the rewards, not only to the people around you, but also to yourself, I think that there's I think that gives you the richest sense of satisfaction. And so to the extent that you can be deploying the intelligence and the drive that you have, as someone who's listening to this podcast, you probably are, in the 99th percentile of intelligence and drive of people. And so you have this amazing gift that you can be providing to the world. And so, if you want to use that to be building trading algorithms, go for it. There's a place for that, and it's important that you're making some money. But if you can invest some of your time, or maybe even a lot of your time, in tackling problems like climate change or healthcare problems, I think that will be really rewarding. And as a starting point, I have some resources in chapter 14 of my book, as well as on the resources page of my webpage, if you're interested in looking at kind of like these social problems that could be tackled with machine learning.
Oh, that's so great. That's such a cool ending, Jon. Very inspiring. Thanks a lot for that, and thanks for being a guest on my show.
Yeah, my pleasure. Vielen Dank.
Thanks, and see you on social media.
Sounds good, Yusuf. Catch you in a bit.
See ya.